I'm Xu Chenchen, and I'm pleased to present my research of unsupervised domain adaptation with pixel-level discriminator for image-aware layout generation. Graphic layout design, which involves arranging various 2D elements, is an essential component for multimedia. In post-layout generation, CGL-GAN leverages inpainting to erase the graphic elements on post to provide the CGL dataset, which has a domain GAN. We propose a generative adversary network with a pixel-level discriminator to learn domain environment features and minimize the cross-domain discrepancy. Both quantitative and qualitative evaluations demonstrate that PDA-GAN can achieve SOTA performance and is able to generate high-quality image-aware graphic layouts for advertising posters. Next, we will provide a detailed introduction to our work from 4 aspects: background, relative work, our method, and future work. Graphic layout design, which involves arranging text, logo, underline, and other 2D elements, is an essential component for various multimedia, such as posts and magazines. An advertising poster design with a high-quality layout is not only well-pleasing, but also communicates information clearly. Early work often utilizes templates and heuristic rules to generate layout, which require professional knowledge and often fail to yield flexible and various layout limited to their handcrafted rules. As deep learning develops, layout GAN, layout VE, and layout weighting appear to produce layout from noise. Meanwhile, some conditional layout generation methods have been proposed, such as attribute GAN, content GAN, and CGL GAN. Content GAN models the relationship between layout element and the image. However, content GAN uses white patch to mask the graphic element on magazine pages and replace the clean image with the proceed patch for training. For the same problem, in post-layout generation, CGL GAN leverages inpainting to erase the graphic elements on poster and subsequently apply Gaussian blur on the whole poster to eliminate the inpainting artifacts. The blur strategy effectively narrows the domain gap between inpainting the image and the clean image, but it might damage the delicate color and texture details of image and lead to unpleasant occlusion or element placement. CGL GAN is the first and most relevant work in the field of image-aware layout generation for advertising poster. Our model is a generative adversary network to learn domain environment feature with the pixel-level discriminator to minimize the cross-domain discrepancy, as shown in the figure. Our network mainly has 2 sub-networks, the layout generator and the pixel-level discriminator. The design of a discriminator can not only finely align image features of these 2 domains, but also avoid the Gaussian blur step in CGL GAN, which brings benefits to modeling the relationship between image detail and layout. The pixel discriminator is connected to the shallow-level feature map and compute the GAN loss for each input image pixel. We utilize one-side level smoothing to improve the generalization ability of the trained model. Compared with the CGL GAN, PDA-GAN has less difference in the generated feature maps between the source and the target domain data. Layout generated by CGL GAN condition on different domains of the same product image with significant difference. In particular, CGL GAN tends to generate layout elements in the inpainted regions. In comparison, layout generated by PDA-GAN with source and target domain data as input are more similar. This analysis demonstrates that PDA-GAN can effectively eliminate the domain gap caused by inpainting. We first conduct an experiment to compare our method with content GAN and CGL GAN that can generate image-aware layout. The quantitative results can be seen from the table. Our model achieves the best result in most metrics, especially in composition-relevant metrics, since PDA-GAN preserves the image color and texture details. As shown in the first column, bounding box of the text elements generated by PDA-GAN are more likely to appear in simple background arrays, which improves the readability of the text information. As shown in the second and third columns, When the background of the text element is complex, PDA-GAN will generate an underlying bounding box to replace the complex background. From the middle three columns, now the bounding box generated by PDA-GAN avoid subject region is nested. Thus, generated post better express the information of subject and layout element. In the rightmost three columns, PDA-GAN generates layout bounding box on the region with low sum values to avoid occluding products. As shown in the first and last row of the table, PDA-GAN outperforms CGL-GAN in all metrics with the same configuration. In the first two rows of the figure, compared with CGL-GAN, PDA-GAN generates text bounding box with simple background. The last two rows show that layout generated by PDA-GAN can effectively avoid the subject array. Our PDA outperforms the DA model across all metrics on the different weights of the DA loss. With the increase in patch size, the layout generation performance progressively improves, mainly due to the discrepancies that arise from inpainting at the pixel level. As shown in the left table, discriminating with shallow feature map in PDA-GAN can achieve better results in both composition relevant and graphic metrics. The right table shows that the model with one target label smoothing performs better in all metrics than without label smoothing. In addition, the effects of the two-side or one source label smoothing are not as real as one target label smoothing. These quantitative and qualitative analyses demonstrate that the lost image details caused by Gaussian blur will degrade the quality of the generated image via graphic layout. More evaluations here. Here are more demonstration of advertising posters designed with our layout. In the future, we may investigate how to better interact with user constraints and enhance the layout generation diversity. Thanks for watching.